Hello, everybody. This is section 5.1, areas and distances. And this section, of course, is part of chapter 5. So we are now in chapter 5. And before we continue with this chapter and close the calculus 1, we need to see how far we are in the story of that we started with. So remember that Newton and Leibniz, their investigation resulted in calculus, and that started with two fundamental problems. One is the tangent line to a curve. So remember that when we started, that's what we started with, is talk about the tangent and transition from there. And the second thing that we haven't seen and now we're going to talk about as we get into chapter 5 is finding the area of a planar region bounded by an arbitrary curve. So when they investigated this, what happened is, of course, the one you saw is the tangent and the velocity problem. Remember that velocity problem where we started with tables and all that? Then we moved into the object motion, and the first derivative is velocity, the second derivative is acceleration. But if you go way back to the starts with the notes, you'll see that we started with tables and see what the values converge to. So we started with that to end up, and of course we used the limits to transition and find the derivative. And we find the formula of this derivative, and from there we built so many other different formulas. So this is what the basis for differential calculus, which is the most important part of calculus, right? Then the antiderivatives in that section of 4.9 gives us a transition. And let's look at the other problem here of the investigating this area under a curve. And for the differential calculus, we started with tangent and velocity. So here we're going to start with the area and distance. So these two problems are going to help us understand how these definite integrals that we're going to work on, what they mean and how they work, all right? And that's going to be the main idea of integrals. And if you look at differential calculus and the integrals, they're going to give us the fundamental theory of calculus. And we're going to see that in chapter 5. So this is kind of the main story. So there is a connection from the beginning to the end. These two charts really shows you the split of the course or of this subject. It's two parts. The two parts are linked. And you see now these antiderivatives, anti-differentiation is the step. But before we continue, we have to talk about these area and distance problems because they're going to help us with understanding what integrals do, right? Just like how the tangent and velocity problems helped us understand the transition to a derivative. And that's it. You'll have the entire story, and you should be able to tell others about it, right? So before we do that, in pre-calculus, often this sigma notation is done, but if you do it or you don't remember it, it's okay. We're going to review for it. So if you see this sigma notation, it means summation, right? So I equal 1, so like from the lower bound to the upper bound, and some people say limit lower to the upper. So of course this is 1 and this is n, and whatever this is gets summed, and each term takes the subsequent numbers, right? So if let's say from the homework 5.1, let's say question 1, it says summation k equal 1 square plus 2 square plus 212 square. What does this mean? Well, the short form of it is k squared, right? And with k equal 1, all right? So if we had this form, we should be able to break it apart to this, right? But in the same time, some other review, some if c is any constant, then if you have for a c, a summation, it just means that many times c plus c plus c, and so it's n times c. If you have c times a1, the summation will use the multiple that way. If you have a summation for a sum, it's going to be the sum of the summations, and same thing for a difference. We have also some other formulas. If you have I and 1, so for example 1 plus 2 plus 3 plus 4 plus 5, instead of doing this addition, you can use the 5 here as n, right? So it'd be 5 times 5 plus 1 over 2, and that will give you the sum of these numbers. So you don't need to, if you have 1 plus 2 plus 3 plus 4 up to, let's say 1,000, we don't need to do that addition. We can use this formula and give us the sum. And this is another one for the I square. It works the same way. So I would recommend you try a few numbers, check them with the calculator and this, and until you become familiar with these and understand how these summations work. One of the nice sequences that you see in upper courses and sequences and series is geometric. And geometric works in a way, and if you're asked for a sum, you need to look at R. R has to be less than the absolute value of R has to be less than 1. In that case, you can use this formula here for the sum. Just like these sums for these terms, same thing here for this geometric series. And you can Google it, watch few videos about it until you become familiar with it. For us, we won't do a lot about it, just to review from pre-calculus and also understand if you're looking for a sum for a geometric series, then R has to be less than 1. If R is greater than or equal to 1, the infinite series does not have a sum. So what else we can see before we move on from homework 5.1 when it comes to this review? If we have, let's say, question 2, just some basic thing to understand how this works. Let's say you have this, and of course this upper thing is let's see if it's defined or not. That's we have to have it. Let's do even this, something like this, so you don't think it always has to start from 1. So for example 3 to 5, what does this mean? Well, it means that k is going to be 3, then it becomes 4, then it becomes 5, right? So we should have 3 terms. So for 3, the first one, we should have something like this. Then we use a 4. Then we use a 5. okay, and so this should be 0, and we'll just do these numbers and try it. You should get negative 258, and let's do a geometric series examples. Let's say this one, find the sum for n from 0 to infinity, and this is a 2 times 0.75n. So in this case, you see that's the form that we have. So in this case, A1 is 2 and R is 0.75. And so we have the absolute value of this R is less than 1. So there is a sum here, and the sum is gonna come from the formula here, A1 over 1 minus R, A1 over 1 minus R, 2 over 1 minus 0.75 is 2 over 0.25 equal 8. So you see this common ratio is less than, has an absolute value that is less than 1. And you also see that this is infinity, right? So infinity means how many terms you can create and add. So this is where these formulas are useful for geometric series, and there is also arithmetic series that you can review. So for our topic here, we're going to start with the area problem. And instead of starting with traditionally the abstract part, let's start with an example. You're familiar with y equal x squared. And let's say we are interested for some reason, but you'll see some physical problems. But in this case, for some reason, we need to find the area under this curve, and we're between 0 and 1. So if you look at it, this area, if you do this 0 to 1, so this is like a square. So the highest this area can be is 1 times 1, you know, like rectangle length times width. So it'll be 1. The lowest it can be if it collapses is 0, like point, right? So to figure out this part, the traditional thing that will help us understand the integrals later is we start with breaking apart this area into these strips. Let's say we decide to divide it by 4. So the width of each one is 1/4. They all have equally divided, so they have equal lengths or widths in this case. And we have S1, S2, S3, S4 strips. And from there, we can decide how to calculate the area based on these strips. So yeah, there are a few options. So we'll see what are the options. We could calculate using the right side, which means you see if you have, let's go to this one that's not done. We could just say, okay, because we're estimating, let's finish it this way. So, and that one I stretched it. So we could be using this rectangles, right? And we know the area of a rectangle is width times length. and the width is 1/4 for each one. They are all the same. They all have the same width. And the length is different, of course, for each one. The height there is 1/4, 1/2, 3/4. And we add all this and we find it to be, because we divided by 4. So that's our 4 and we're using the right side. So 0.46875. And of course, because we use this right side, what the area we're looking at is a little bit higher than what it is, right? So this is maybe overestimating. So the area we came up with is greater or bigger than the actual area. We can now do a different approach. We can calculate another way. Not, you see, this is the first one. So maybe we can use this one. So this is the first one, and this will be the second one. If we use the second one, as you see here, the first one collapsed because of, if we're trying to just get this, but not get it from the top. And you can see here, it's easier to see with this ones here. So same thing. The width is the same. And we use the height, which is here the length or the height here for these rectangles, 0, 1/4, 1/2, 3/4, and that gives us 0.21875. So what happens is we do it one way, we're overestimating, and one way we're underestimating. So the actual area is definitely between these two values. And this picture will give you that. So 0.46, this one gives us 0.469, and this one gives us 0.219. So the area is somewhere here. Between these two numbers. So that's the important part we're going to be discussing as we move forward. So if you see that we divided by 4, so the more you divide, which means the more strips you have, the better estimation you're going to have. And using the left end points and using the right end points, so as you see, this kind of increases, and when we use the right end points, we have an overestimation, and when you use the left end points, while this is increasing, you have an underestimation. And so if we divide more, we use L8, so we use, let's say 8 strips instead 4. These numbers start to get better, improve. So instead 0.46, 0.21, you see how apart are these two. Now 0.27, 0.39, the gap starts to improve. So let's say now with the n, it gets even bigger. So we say Ln or Rn for the right and or the left, and how many strips we're using for this calculation. So the more we have, the better estimation we have. So you can see that for 50, 0.32 and 0.34, but with the 1,000, it's 0.3328, 0.33. It's like they're converging to a number which is this. So that area, by taking more strips, we converge to the correct area. So that's geometrically kind of giving you the picture here. With using a 10, with using a 30, with using a 50, and the right end, of course, produces upper sums, because these x square increasing, and the left endpoints produce lower sums because, of course, in this case, it's increasing. So that's important to double check whether it is increasing or not. So I think now you have a kind of a good idea that that if we have a curve, right? And if you're interested to calculate the area under this curve, you're going to try to get some equally lengths, right? So it's like these rectangles. So this is the beginning of understanding what's happening. And we're going to do the sum of these areas. And this sum is supposed to give us that calculation. But you see, of course, the challenges in what we pick. So we get to the definition. We've seen if you divide two more strips, you'll get a better approximation. So if we want to get to that exact number or as close as possible to it, we should take the limit, for example, to the Rn, which is the right end, using the right end points. And this is the same thing, the width times f of x1, remember the y, the height, which is the y, or of course for the rectangle is the width, and the same. So we multiply these two and we add them up and we take that limit. And of course the function has to be continuous, and if it's continuous, the limit exists. And we can also do the same thing for the left limit, except for the difference on what you use for. Here it's 1, but here it's 0. So that's what you need to see, because you're using the left. So the first one here is x0. If you're using the right end, then you start with x1. And we'll see this in examples. But the main important here is to understand what's happening. Or we can take an xi number. So for the length, which is like the height for the picture, instead taking the left one or the right one, we can take xi star, which is whichever we think is convenient for calculation. For example, we can take the midpoint, right? We can take maybe the midpoint for each one, and that will probably help better. So if we do whatever point we're taking, left, right, or here in the middle, or somewhere where the graph is, right, where the graph intersects these are called the sample points, xi star. So you can use the xi stars, and those are sample points, and they could work for each part, for each rectangle, maybe where it's intercepting the curve and get the accuracy to a better form. In that case, the area is the limit. You see, not Rn, not Ln, but f of x star times delta x times the width. All right, so in general, to solve this here, to solve this area, and we're going to talk about distance as well. So to solve this area problem, well, you're going to divide or partition the interval into the interval AB that is given into n equal pieces. So you get delta x as a width of these sub-intervals, b minus a divided by n. So the ends for the interval divided by n. So the subintervals are going to be from x0, so a to b, and so the first one is going to be x0, x1, x2, and so forth, until you get to xn, right? And this is going to be delta x, and this delta x is found by doing b minus a over n. So after you do that, you can now add the area to the left or the right. So it depends. So there are two methods, and we'll see these two in the exercises. Or you can take the limit as n approaches infinity to find the true area under the curve. So you can take this limit. So, and I also mentioned that instead using the left end point or the right end point, you can also use sample points. And the sample point could be where the curve is intersecting each rectangle, or some people also use the midpoints. So that's one thing we're going to be solving. Maybe before that, so there is a problem here. We're going to solve, but mostly we're going to focus on distance problem, and we're going to use that idea here in it. So let's look at the distance problem. It's a nice problem. This is just a quick thing. Just to remember, when you say miles per hour, that means the rate is miles over hours, which means the distance over time. So remember this part. So the distance is the rate of speed times time. So this is just to connect it with this. Why are we doing something times something else for distance? Well, because you've done it all the time. The distance is the speed times time. It just here the terms, of course, are more precise. We're talking about velocities and talking about time as intervals. So if we consider this problem here, the distance is the velocity times time, right? But if the velocity varies, it's not easy to find this distance travel. So remember here for calculus, it's dealing with curves that are changing, the rates are changing. So that's where the challenge is. So let's look at this example. Suppose for this car, this odometer here is broken, and we want to estimate the distance driven over a 30-second time interval. We take this speedometer readings every 5 seconds and record them in the following table. So we have time 0, 5, 10, and so forth with seconds, and we have velocity as miles per hour. So you can see that these don't match. So one thing we will definitely need to do is convert these units, and for the conversion you can use this formula here because of the mile to feet is 5,280, and the hour to seconds is 3,600. So we will multiply, for example, 17 times 3,600. That'll give us that, and you do the same thing, 21 times 5,280 over 3,600, and we'll switch to have consistent units. So watch for that. If you don't have consistent units, you will need to convert. them. If you have consistent units, you just keep going. So for this example, it looks like we have time from 0 to 5, and I will do one in the homework and explain it even better than how this one is done in the book, because here you're given a table, but they're not using the rectangles to show the area under the curve. But let's show this one, then we can do the other one. So remember that if you want to figure out here for the let's break it apart, and can explain the other one. So during the first 5 seconds, the velocity doesn't change very much, so we can estimate the distance traveled. So remember, our goal here is the distance. So what will happen is you have a curve, right? And we have these rectangles we are interested in. And that's exactly what's going to happen of, let's say you have time and you have velocity. Two things you're going to multiply, and you're going to get the rectangle there, which once you add all the rectangles, they're going to give you the total velocity, the total distance. So that's how these two are linked. So if we take the velocity during that time, the interval to be 25, if we obtain the approximate distance traveled, then we're doing 25 times 5, which is 125. So what will happen as you look at this curves, maybe we should switch these to a graph, and that's going to be helpful. So I did this graphs to show you how it works, because it could be confusing from the table. Looking at the table and coming to this may not be that clear, but we know now what we're looking for is the area under this curve. So this curve is the velocity, so we want the total distance. And let's start with the left. Let's say we're looking for the left, and we have 6 here. So this first one is here, right? So that's the area of, this is the first rectangle, and that's the second one, and 35. So that's next one. That's next one, right? And that's the next one, and that's the next one. So you see this is not increasing, so we can say whether overestimate or under. So these are the rectangles that if we add them, we're gonna get an idea about the area under this curve, which is the distance we're looking for. Here the width is the same, is 5 for each. And so for this first one, it's going to be 5 times 25, right? And this one is 5 times 31. And this one is 5 times 35, I think, there. And this is 5 times 43. And this is 5 times 47. And this is 5 times 45. These areas, so the length times width, and we add all of them. So this is that, right? So that's how they came up with this one. And you do the sum, you get 1130. That's one way. We can do the other way, which is the right side. the right side, and 6 of them. You see the right side now, this is the first interval, but we're starting with the 31. Then the next, then a 43, and this one here. So we have 1, 2, 3, 4, 5, and 6. So as you see, the width did not change. It's same 5, but here the length is 31, right? Like the height here is 31. Here 5 times 35, 5 times 43, 5 times 47, 5 times 45, 5 times 41, and that's going to be matching this, right? And that's 1210. So we have 1130 and we have 1210. And of course here you're not going to come up with the conclusion of over or under because of this is not the increasing curve. So so just look at we can put them next to each other and see that they are not the same curve, the same interpretation or calculation to the area. And of course, we look from the numbers that they are not the same. So moving forward, we can do that, of course, delta t b minus a over n, and use these things, and we will see in the examples for the distance problem, and we can use the left or the right, and of course to get to a good, let's say a true value of something, we can get that distance using the limit for the same operation that we did. We did the sum of these strips. So the sum of the strips, and you take the limits, which means as so many strips as possible to get the true value of a distance. So we'll practice a little more doing example 6 from the homework here. And we have, for this one, I dropped the graphs already to explain it. You don't have to do the graphs, but they help for the visual and understand what's going on. So estimate the distance traveled by the motorcycle during this time period using the velocities at the beginning of the time. So the beginning means the left, right? And so we have, a quicker way for the left, of course, you're going to start with the first one. So we have a 32, and we have next a 28, and we have a 25 and a 21 and a 24, because we started from the left. So this is not going to be picked up in times 12. So that's a common factor, because 32 times 12. So just like these, you see 25 plus 31 plus 35 plus 43 plus 47 plus 45, they all have a common factor of 5. So same thing here, and that will give you 1560. All right, and you can do that here on this graph if you want to practice it and see how that works. You can say if this is the, if I'm using this, then this is the first. So that's, and that's the height is 32. So 32 times 12, 28 times 12, 25 times 12, 25 times 12, 24 times 12. Okay, so we can do the other way for B. Give another estimate using the velocity at the end. So at the end, that means now we're going to switch. So we're going to pick up this one. So we will start with this in order to pick up that one. So 28, 25, 21, 24, 27, and times 12, and that's 1500. So are your estimates here in parts A and B upper and lower estimates? We don't know really because of this function or whatever trend we're looking at is not increasing. It has to be increasing for us to say that. All right, next example, and so please try it. So try this, try it. So you start understanding the sketching part and how it works, and then you do the calculation for the right side. All right, so we have 1, 2, 3, 4, 5. So all as well here, so try like R5. And that's what we did, 1, 2, 3, 4, 5. So let's call it R5. Let's do another example from the homework. The velocity of graph of a braking car is shown, used to estimate the distance traveled by the car while the brakes are applied. Use M6. So we're going to use some sample points, the middle, and there are going to be 6 of them. All right. So let's go here for, we need 0.5, we need 1.5, 2.5, 3.5, 4.5, and 5.5. Right. And so that's going to be about 82.5. That's a 60. That's about 42.5, 42. That's not the 30, close, 27.5, 27. And that's the half, so 15. And that's a little less, so it's a 6. So that's And once we do the mid here, the midpoints, right? Then we see that it's these is 1. You see this between 0.5 and 1.5, that's 1. So delta t here is 1. Delta t is 1. And we can go ahead and just say M6 is, of course, that delta t times whatever values you find for 0.5 and 1.5 and 2.5 and V for 3.5 and V for 4.5 and V for 5.5, which is 182.5 plus 60 plus 42 plus 27 plus 15 plus 6, and let's see what this comes up to. 232. .5. So the velocity graph is given. Use this to estimate the distance traveled by the car while the brakes are applied. And that's it. So for this decreasing, so we can see that this is a decreasing function, right? So for this decreasing function, if you use, if we use the left endpoint, if we use the left endpoint as the other examples, or using the right, we're going to overestimate. And if we use the right endpoint, we're going to underestimate, just like we did for the other examples. We have the reverse here. So using these midpoints is going to give a better estimate to this distance that was traveled during the braking. Okay. Last examples here, we're going to do a little bit quicker these, and I kept them the way they are because they could be much challenging, because if you're going to look into what is the general formula, because these don't have a unique kind of solution. So it is good that it's a multiple choice. If it's multiple choice, that means you're given one correct choice. But if it's not multiple choice, then there is different answers to it. So looking at this and having it multiple choice, it looks like this one is possible, and this one is possible because that's the ones that have exponent 10, right? But of course the interval decides, and let's look at it. So if we say this is the area under a curve, let's say this curve here, right? Then what does this mean? It means that delta x, of course, b minus a, 2 minus 0 over n equals 2 over n. Then delta, then xi is going to be that first one, which is the 0 here, which is a, plus I times delta x, and 0 is 0, and I times delta x, we just found is 2 over n, which is that part. Yeah, so this is, so yes, so let's erase this one. And for this to be correct, I think it needs something else. It needs a different interval. It needs like a 5, a 7 interval. So if somebody is interested, so for this to be correct, it needs like this type of interval for it to be correct. So that's maybe extra thing to look into if you're interested. Similarly, we're going to do for this example, and it looks like this area is going to be under, let's see, this curve, right? Why? Because similar thing, you're going to do the delta x is pi over 6 minus 0 over n, which is pi over 6n, which is that. And you know the I is going to come from xi equals 0, which is the first one, plus I delta x, and that's I pi over 6n, right? So